So this all started about a year ago. So winter was already underway where I live in Stockholm. It was cold and gloomy. I don't need to tell you more. Like you've seen the weather outside. It's the same weather. Leaves were starting to fall. It was like almost already snowing. And then, like all modern new cool stories, it started with an email. This is the email. So I like playing games. It's actually one of my main hobbies. Or rather, if I'm honest, no, like the hobby is not playing games. The hobby is buying games and then just contemplating them because I don't have time to play anymore. But during that sale, I picked up a game called Potionomics. It's the first game by a small game studio, and in it you play Sylvia, that we see here, who she inherits her uncle's potion shop, and along with that she must pay off. And to do this, you, as Sylvia, you have to make potions and then sell them for the highest price possible. So little did I know that this would take me into like a whole like rabbit hole that I did not see coming. They all start like that, and it somehow involves Ruby. So hi, I'm Youssef, and I'd like to drag you with me today in this rabbit hole and see what we can do. So part one, on what is Potionomics, I have to explain some of the core mechanics. So a large portion of the game revolves around Sylvia making potions from ingredients. So it's a little like that. So you have ingredients like this, and the ingredients have different elements. So for example, you have this fayberry here. It has 6 different possible elements from A to E, and the fayberry has, for example, 6 of A and nothing else. And the mandrake root has 6 of B and nothing else. So these are, you're gonna see these all over. And then to make potions, you have to mix the ingredients so that the ratios of ingredients, of elements, match these ratios here. So for example, a health potion is a potion that has as much A as B and no C or D or E. And the mana potions is the same, but with B and C over there. And to do that, you have this cauldron, and then you have to mix the ingredients together. So we're gonna do this, and you have like the cauldron has a maximum amount of ingredients that we see here, and also a maximum amount of elements that you can mix that we see here. And throughout the presentations, the ingredients will be the strawberry emoji, and the ingredients, the elements, the little potion. So let's try to make a simple potion to get a feel of how this is like. So we have an empty cauldron. We're gonna add 1 fayberry. So we add 6 of A, and then we have 1 ingredient consumed and 6 elements consumed. Then we're gonna add another fayberry. That's 2 elements, 12. That's 2 ingredients, 12 elements. And then we're gonna add 2 mandrake roots. And now we have 12 of A and B, which means that we have the right ratio to make a health potion over there. And then there we go. We have a health potion with 24 elements. And also, by the way, this is one giant keynote slide. So anyway, so our goal is to making good potions, and this has 2 sides. So one is making potions, which means respecting the ratio and having the ingredients fit in the cauldron, and also having the components fit in the elements fit in the cauldron. Also, you have to use the elements we have, the ingredients we have. And 2, you need to make them as good as possible, which means you have to maximize the amount of components. So you have to make the number go up. And then where it gets complicated is as you play through the game, you get more different. These are new potions that you can make, and look at the ratios there. They're not as simple anymore. So you have like 3 to 4 to 3, or like 2 to 1 to 1. Then you get bigger and bigger cauldrons. You can use up to 12 ingredients with 900 elements here. And then you get ingredients that are completely wacky in the proportions. So like 1133 to 33 or like 96 to 48, and then you get like a backpack that has like a huge amount of ingredients and ah. So this is where I was like, like I don't want like so the game expects you to make good enough potions and like just play around with the like you would do in witchcraft, like but that was not good enough for me. Like my engineer brain was like, no, good enough is not good. So this is where I started like, okay, can I do something? Can we find a way to make the optimal potion somewhere? So I picked up Ruby, and you start with representing the problems. So you have these like basic data structures, a composition which represents the little like mix of elements, and then we have a potion that has a name and the target composition, ingredients with a name and composition, and combination, which is like an array of like ingredients, and a constant with like how many ingredients in the cauldron. And then once we have these basic data structures, we can declare some operations on the data. So for composition, you can calculate the total amount of elements. You can add the composition to another, and then you can just compare two compositions to check if they're the same. And then the third part is you build the data from what the game gives you. So you start entering the different ingredients that you have. So you have like the fayberry, and here is the serpent's slippery tongue. And then you start declaring your potions with the target compositions. So here's the two potions that we saw. The health potion with like A1, B1, C0, and the mana potion with B1, C1, and no A. And then lastly, you build what you have in the backpack. So it looks like this, with the elements on the left being potions. And I'll just represent them like this with the little icons. And then how do you, like, you have these data structures. How do I now go from this to actually finding what the optimal potion is? So we have to go from this is our backpack, and you have to transform this backpack into a way that we can combine things. So what we do is we transform it into a flattened array, where like we duplicate each item in the backpack. And it's done like this. And then from there, we need to go and from the backpack, make all the combinations that have 6 elements in there, because our cauldron has only 6 spots. So we want to have something like this. This is also handmade in Keynote. So yeah, so we have to have this. How do we do this? It turns out that Ruby helps us. There is a method on enumerable called combination that does exactly this. So this looks like just you take all combinations, you take the inventory and you call combination with like the number, and then you transform it into the objects. Then from there, once we have all the possible combinations, we look for the ones that satisfy the proportion to make a potion. So we take all of that, we filter it, and then we get that you can make a health potion with these 3, and we can make a mana potion with this combination. And this is done like this. It's like the least readable code I have here. But yeah, you can do that. So we tried that, and it looks like this. You get all combinations that are possible. You combine them, and then you find that you can make 1 health potion and 1 mana potion, and then the program gives you the little the ingredients that you need to pick. So yeah, there I did it. Like I could optimize my potion brewing. So then I started using real data. So I put all of the ingredients in a big Google sheet. I exported into a CSV. This is what my workstation looked like when I was playing the game. By the way, like one day my girlfriend came back from her work and she saw me doing this. She was like, "Oh, like I'm sorry, you're still working." I'm like, "No, don't you see? This is how I relax after work." Anyway, so I got all my Google Sheet with all the ingredients I have here, all like color coded by measurements and everything. And then I run the program, and it just hangs. And it's like it's been hanging for like 30 minutes. I'm still staring at the screen, playing my game. And I was like, why? Why is this? And we all know that's because Ruby doesn't scale. So I rewrote everything in Golang, and it worked. No. So the reason it didn't scale was this: we had this typical combinatorial explosion on our hands. So in our prototype, we had 6 ingredients out of 9, which is 84 combinations. You go a little bit into the early game, you get 100 ingredients, which becomes like 6 ingredients out of 100, which is 1.19 billion. Still manageable on like M5 Max Pro Ultra, whatever. But in the late game, you get 11 ingredients in a cauldron that has 1,200 elements possible, and that's a huge amount of combinations. So just to give you an idea of like what 1.9 to 10 to the 26 is, you take a single sheet of paper. If you stacked this many sheets of paper, that's more than the observable universe. So I was not going to do this like this. And by the way, this is a version of a computer science problem called the knapsack problem, which turns out is what we call NP-complete, which means that if I ever solve this quickly, I am eligible to $1 million prize, and I can break crypto. So no. So we had to think of something else. And the way that I want to shift is that I want to like see two characteristics of this problem that make it eligible to have another way. So the first one is that we have this concept of target values. So we want to maximize the amount of elements by changing different variables. So we have a target value with variables that we can change. And 2, the observation that all our constraints are linear. So for example, if we take the constraints that we have are that we have to make this ratio with these kind of elements. And those are kind of the constraints that we have. So we have the ratio is that 6 Fayberries should equal to 6 green thingies. And then we have you have to respect the cauldron's maximum capacity in elements. So you have 6 times the elements is inferior to something. So when I say linear, it means that this only has multiplications and additions. Multiplications by a number, and additions. No squaring, nothing like this. Our other constraints are that we have to respect the cauldron capacity. And then lastly, we have to respect the backpack capacity, so we don't use more than we have. So now that we have these 2 characteristics, so we want to target the value, maximize the value, changing variables with everything being linear. We have a tool in our toolbox called linear programming, which takes us to our third part. So what is linear programming? So it's a method to achieve the best outcome, such as a maximum or a minimum, in a problem that has only linear relationships. So it's exactly the kind of problem we have. So technically, it's integer linear programming because we cannot have 1.5 ingredient. And this is actually a really, really active area of research because since we can't solve this in a general way, people have developed heuristics to try to cut down on the solution space without exploring everything. So from theory to practice, now we're gonna see how to go from this to actually solving the problem. So there's 2 steps. There's describing the problem is number 1, and then 2, finding a solution. It's this, but it's also general life problems. So the first thing is we have to describe the problem. There's a file format called the LP5 format, like LP for linear problem. Sorry. And it looks like this. It's kind of a DSL. It tells you exactly what you need to do. So like you write, I want to maximize some equation, linear, always linear, subject to some constraints, and then you give some bounds to the variables and then end. And then once you write this, you give it to solvers, and solvers are like they're only made to solve these kind of problems. So the biggest one is the IBM iLog Cplex. You can tell it's IBM because the logo has 3 different names with 3 different typos, and like it's like all over the place. It's been around since like early 80s, and it's been like developed to hell, and it's really, really expensive, and also really, really efficient. And then there's the new kid on the block on this solver space, which is Gurobi. They're competing directly with IBM on the really, really expensive Colas for enterprise, and you pay by CPU core still. And then there's the GNU project had this linear programming solver, and you can tell it's the GNU project because there's no logo. It's called GLPK, and it works on basic problems, but it's pretty slow. It's pretty old, and you start getting into these problems, you're already like looking at pretty long solution times. And then the last one is called CBC, the last big player. It's an open source project that has it's like good capacities, and it's between the GNU, like GLPK, and the big commercial solvers. So it's a good compromise. And then there's a gem that interfaces CBC with Ruby, called Ruby CBC. And that's what we're going to use. So we're going to try to find a way to describe our problem and then solve it using this new method. Then once you get into this space, then everything becomes much more readable. You don't need to think about the combinations anymore. So we start by creating a new model, and then we declare our variables. So the quantities are the quantities we're going to use for each ingredient. And then from this line, you're going to get this is a map. So you get an array of Ruby objects that symbolize an unknown quantity that we're going to try to set a value to later. And then once you have that, you can play, like those are normal objects, so you can take this quantity that you don't know the value of and do like additions and multiplications with it. So what we can do, for example, is those are elements per type in Cauldron. I'm just going to use ABC for now to simplify, but it's the same thing. So you have these quantities, and then you can multiply them by the composition of the ingredient, and then you can sum everything. That'll give you the total elements on your Cauldron. Again, you don't know what the quantities are, but if the quantities are this, then you can just like sum, they call a normal sum, Ruby sum on it. And then the objective. So what do we want to do with this? We want to maximize the amount of total elements. So how do we write this? Well, that's it. That's like you don't have to write anything more than this. And what else? Like, so you still have to describe the constraints. So you want, for example, the sum of the quantities to be under the max elements of the cauldron and the max ingredients. How do you write this? It's the same. You can totally read this. It's like almost like magic that you can actually write this. And the last thing is that we want to describe the constraints of like having like the backpack constraints. So like this is a bit more complex, where you have to loop through the backpack to the quantities in your backpack and just set that the quantity is less than the backpack quantity. So here, second line. And there is one thing that's a bit tricky, is that for potions we have this ratio constraints with like sometimes more than 2 or more than 2 elements. And then here you have to, for example, if you have like 1 to ABC in a ratio to 1 to 2 to 1, then you have to convert them into different, into multiple equations. So you transform this into this. So you have two equations, and then you can write this. I'll skip this. Yeah, and then once you have this, you can generate an LP file using this by generating a problem. How do you write this? Yeah. And that outputs actually an LP file that looks like this. So we can go through it. So we want to maximize this is the target for the measurements, or like the elements. To maximize our target function, while given, like, this is the max ingredients constraint. This is the max measurement, like max elements in the cauldron. We want to enforce that C equals 0. This is A equal B. So these two equations here are the constraints for the ratios. And then here you describe your inventory. So I know I have 3 and 4 and 2. And then here you just want to make sure that the ingredients are positive, because otherwise, like, the solvers might go for like minus 95 ingredients. And then how do you solve this? Like using CBC, like output something, I don't know. Do this. And then what we get is immediately, like, it works. It's like, and I also implemented a little thing where, like, it tells you the quantities. This helps me update my Google Sheet, which has now my new game screen. It also works when the combinations become pretty big, and it runs in like half a second. This optimized for 968 measurements and for like some weird ratios too. So yeah, we did it, or like I did it in my room at 4 a.m. I am now a master potion maker, and thanks to linear programming, I could get the optimal potion every time, which was extremely satisfying. I like run through the game like I almost speed run it if you don't count the programming part. It was also 4 a.m. and I needed to sleep. So some parting thoughts. One, declarative languages are magic. It feels almost like cheating when you find a tool that like speaks the same language as your problem. It trivializes the problem almost. So other examples of this are SQL, where you don't need to think about how to retrieve the data from the database, or Prolog, if you ever looked at this, is like just the language does the thinking for you. And I want to give you a quote by Soren Johnson, which is the creator of Civilization. It says, "Given the opportunity, players will optimize the fun out of a game." So is this true? For my case, I actually don't think it was like it was no. It's not that I don't think it was. It was not at all, because it's like I made a new game for myself, like outside of the game. I created another layer of problem solving that was like actually really satisfying. 3, play Potionomics. The part I showed you is only a small part of the gameplay. It's also a deck building game where you have to sell the potions, and has a really nice, wholesome story. And yeah, one more thing. So it's all fun and games, as we've heard before. But I want to leave you with one serious application of linear programming, so that we know that this is not just for potion making. So I want to talk a little bit about linear programming and energy modeling. So energy modeling is a research field that's used by policymakers for a region to plan for regions' energy needs. So you can use it at all scales, from like small scales like neighborhoods. Like you can plan how much your energy, electricity, or heating your neighborhood will need, or larger scale like continents. And this problem looks a lot like what we have. So you have an objective function. For example, you want to minimize the total energy generation costs, or you want to maximize the system efficiency of renewable energy utilization. You want to minimize environmental impact, for example, by minimizing CO2 emissions. So you pick your target function, and then you have variables to play with. For example, energy generation levels from different sources, like what we call the energy mix. How much coal, solar, gas, wind you're gonna use at a country scale or at continent scale. Also, you can play with the energy storage and distribution amounts, how much you can, how much you can plan for in the future. And also, you're also subject to constraints. So for example, you have limited energy demand, or like you have to exactly match for electricity, for example. Supply has to equal demand at all times. Or you have your capacity limits for electricity generation. You have some limited renewable energy availability, or you have some emission limits that you want to keep. For this is like a whole other area. And there's like commercial solutions, like Plexos and AAMMS something. And what they have in common is this button, book a meeting with us, talk to sales. These are sold to governments. So like Sweden has, and other like European countries, they all have like either these commercial solutions or build them in-house, but mostly they're commercial. But what if you can't afford one? What if you're Kenya or Uganda or Costa Rica? Like you cannot afford these solutions and you're not trained to even use them. So there's this energy, like open source energy modeling system, which is an open source version of these solvers that uses behind the scenes exactly the same technology that didn't done for the potions. Like it uses CBC and uses LP files. It was actually created in 2011 or ish. 2010. There you go. And it was created in KTH in Sweden, where I live, by a man called Mark Howells, which is the first author there. This was his, I think, his PhD project. And since then, this has taken a whole life. This project has taken a whole life, and it's been used by many organizations. So we see the UN here. We see different environmental institutes throughout the world. And for example, what the UN is doing with this is that they're taking this project, open source, using CBC, linear programming, and they're going to countries that don't have the capacity to use commercial tools, and they're forming the decision makers to use this and to use this to plan for their energy needs and like all different levels of scales. But they did have one problem. So in order to run this, the models are run in Python. So you go there, like you go to their workshop, then you have to run a console and like install Python. And people have like, decision makers are not technical people. They are like, when you put them in front of a like Python console, they're completely lost. So when the UN used to go to these workshops, they would lose like 1 to 2 days out of maybe 5 to just like setting up the environments, sometimes on like old Windows XP machines. So like you're gonna ask me, how do I know all of this? So in a previous life, I was an energy researcher actually. I did my master's thesis in the KTH lab that made osmosis. This was my master's thesis. And Mark, the creator of osmosis, was my supervisor. So after I saw this problem, like I was already working in the industry, in the web industry, I met with like someone in his lab and we talked about these problems where like people had to install Python for like 2 or 3 days. And I had this idea of like, what if we did something on the cloud? So we have this project, we work together on this project called Osmosis Cloud, and it allows you to run energy modeling systems in the cloud using AWS instances to do all the calculations that can take up to like multiple hours sometimes to run. And we collaborated with the UN and created this project. And so this is a platform where anyone can go and run their scenarios and run their energy modeling systems. And it's all done in Rails. Thank you.